Hello guys, so welcome. So first of all, a small caveat: if you don't know any of the tools or theory I'm going to be using in this video, then check out my YouTube channel then, because there I give full-on lectures on every single tool or theory that I use. And right now, ladies and gentlemen, 2009 USAMO problem number 4. N is greater or equal to 2 AIs are positive real numbers. Also, we are given that the sum of all the AIs multiplied by the sum of all the reciprocals of all the AIs is less than or equal to n plus a half squared. Yes, right. You're supposed to prove that the biggest number that appears amongst all of the AIs is less than or equal to 4 times, so I guess quadruple of the least number that appears amongst all of the AIs. And I have absolutely no idea why Americans love maximum and minimum functions so much, but we'll get rid of it in a second. So what I would like to do here, first of all, is get rid of those maximum and minimum functions by assuming, without loss of generality, kind of an ordering here. Yeah? So I would like to say that A1 is less than or equal to A2, which is less than or equal to A3, and so on. And A sub n will be just the greatest one of all the AIs. Awesome. And so, this actually reduces my statement to just proving that the maximum number, so an, is going to be less than or equal to 4 times a1. Yes, so that's what we would like to prove right now. Awesome. So, after getting rid of those maximum and minimum functions, maximum functions, what we're going to do is we'll try and make use of this thing we have given by the problem statement. So, this upper bound on the product of those sums. So I would like to maybe try and get some kind of a lower bound for this sum. Well, maybe then I would be able to use this thing to my advantage, solve the problem. And the problem is that, how am I supposed to get some kind of a lower bound for this product of sums? Well, Cauchy-Schwarz inequality, product of sums. But the only lower bound I could get using Cauchy-Schwarz here is just n squared, which is absolutely not sufficient, because what I'm going to get here? N plus a half squared is greater or equal to n squared. That's not the ideal scenario, I guess. Yeah? So I would like to actually introduce a nice trick here. So instead of multiplying sums that look something like this, so a1, and I'm adding a2, and then I'm going to be just adding stuff up to an, and then I'm going to multiply this stuff by 1 over a1, then 1 over a2, up to 1 over an, because the only upper bound and the only lower bound I can estimate for this one is just n squared. I would like to go on and swap a sub n and a sub 1. It's not going to change the value of the sum at all, because I'm still adding the same numbers and changing the order of the things I sum up, it doesn't change the sum eventually. Yeah, so I would like to swap a sub n and a sub 1. So the order would look something like this: a sub n plus a sub 2. Then I'm going to be adding all of this stuff in the right order. And then the last thing I would like to sum up is a sub 1. And I'm going to multiply it by, the same sum as before. I'm not changing anything here. So 1 over a1, 1 over a2. Everything multiplied by 1 over an. Lovely. So what kind of lower bound I can estimate on this one? Well, using Cauchy-Schwarz inequality, first of all, I have to multiply the first term here by the first term there. So what I'm going to get is, first of all, the square root of a sub n times times 1 over a sub 1. Yeah? So an over a1. Then, a2 over a2, a3 over a3, up to n minus 1 over n minus 1, so I'm going to get, I guess n minus 2 ones, because I would get n ones if this was in the right order, but I swapped two numbers, I'm going to get n minus 2 in the final sum, so n minus 2 ones. And then the remaining square root of a1 multiplied by the reciprocal of an, and then I have to square all of it. So now I could actually go on and nicely kind of make a chain inequality by this stuff and also this stuff, getting in the end that n plus a half everything to the power of 2 is going to be greater than or equal to the square root of an over a1 plus n minus 2 and then plus the square root a1 over an, everything to the power of 2. Now, the nice thing is that we can just go on and kind of simplify it by taking the square root on both sides. Those ends are going to cancel each other out, then I can move that 2, and what I'm going to be left with is just, well, after cancelling out those ends, 5 over 2, and that's a bell ringing, is greater than or equal to the square root, actually I don't need the parentheses there, the square root of an over a1 plus the square root of a1 over an. Well, that's actually starting to look like something workable, which is absolutely lovely. So now I guess I can just go on and erase that proof, that problem statement actually. Yes, so I will erase everything up until this last bit of my patience also. So well, now it would be kind of nice to go on and square both sides to get rid of those square roots, and actually to work out pretty nicely, because after squaring everything that I will get 25 over 4 on the left hand side, and here I will get just an over a1 plus a1 over an, and then plus, well, 2 times the square root of an over a1 times the square root of a1 over an, but this stuff right here is just going to be a1, so that's going to be just a2, which basically means that I can just go and erase this stuff here and just say that I'm adding a -2 to the left hand side also. So that's actually going to be 17 over 4, 17 over 4 greater than or equal to an over a1 plus a1 over an. Awesome. Okay, so let's get those to a common denominator. I guess it would be nice. So there will be no problem in multiplying everything by a1 times an, and that's because, well, those are just two positive real numbers, so it will not change the sign. It will not flip this inequality sign by any means. So this is gonna be 17 times a1 all over 4 greater than or equal to an squared plus a1 squared. And after getting everything to the right hand side of this inequality, it will be a1 squared plus an squared negative 17 over 4 a1 an. That's gonna be less than or equal to 0. Actually, maybe let me get fancy here. I will take an orange chalk. Oh, awesome. To separate it from the stuff I wrote earlier, yeah? So that 0 is too small. Awesome. Now, actually, there's pretty neat thing here, because, well, we would like to prove that a1 is greater than, is less than or equal to, well, what? No. We'd like to prove that an is less than or equal to 4 times a1. And so there will be absolutely no chance of doing that unless we get this right-hand side to some kind of a product form. Yeah, we have to make it a product of some two linear factors. Yeah, and actually there is a nice way to do it, which you probably just would have to kind of play around with for a while, and that's 0 is greater than or equal to, well, an minus 4 times a1 multiplied by an minus a1 over 4, which is actually pretty nice thing, because, well, this stuff right here is always, absolutely always greater, is always greater than 0. As I saw, well, that's because an is greater than a1 also, so this is absolutely greater than or equal to 3 over 4 times an, which is a positive real number, so it can be 0, yeah? So this thing has to be, well, it has to be less than or equal to 0, which basically means that an is less than or equal to 4 times a1, which is what we're supposed to prove. Ladies and gentlemen, yeah, try to record it 3 times or 4. No idea, I'm brain dead by this moment. Anyway, hope you enjoyed it and see you in the next one.